Hello everyone, my name is Francis Arevalo. I am a fourth year CPE student at Bicol University, Polongi, and in this video I will be discussing laboratory activity number 8, sampling and aliasing. Now, sampling is the process of converting a continuous time signal which exists in real world into discrete time signal that a computer can process. Now, we can take these samples at regular intervals determined by the sampling frequency or f of s. Now, the time between samples is Ts, or Ts is equal to 1 over Fs. Now, according to the Nyquist-Shannon sampling theorem, a signal can be perfectly reconstructed if the sampling rate is at least twice the highest frequency component of the signal. Now, the formula is given as f of s is greater than or equal to 2f max. Now, if this condition isn't met, the aliasing occurs. Now, aliasing or distortion happens when higher frequency appears as false or lower frequency signals, distorting the waveform. So this is the source code for laboratory activity number 8. So the first thing that we always need to do is to import the necessary libraries. Here we use NumPy and Lab8. Now, first is we create a continuous time signal 5 Hz sine wave. So this is the continuous time signal of 5 Hz sine wave. So now let's try to sample it at two different kinds. So here we have two different sampling frequencies. The first one, or the FSI, represents the frequency which is higher than the Nyquist rate. Here we have the frequency of 50 Hz. And for the second one, we have the Fs low, or the frequency which is lower than the Nyquist rate. Here we have the frequency of 6 Hz. So below are the sampled signals. Now, N high and N low represents the time array or the time samples, and X high and X low is the sine wave or the sampled sine wave. Now let's plot the signals. Here we plot it using matplotlib, and for this example we will use the dot plot and the dot stem, because we use the dot plot to create the continuous time signal and dot stem for the discrete time signal. So let's run the code. So this is the output of the two sampled frequencies. So the first one represents the proper sampling at 50 Hz, and the second one represents the undersampling at 6 Hz. So when sampled at 50 Hz, as we can see, the red one represents the time samples, and the blue continuous wave line represents the sine wave. So when sampled at 50 Hz, as we can see, the waveform was captured smooth and accurately. Now this is because the sampling frequency is much higher than the Nyquist rate. Now, when we look at the bottom one, we have the undersampling at 6 Hz. Now, at 6 Hz, the samples no longer represents the true waveform or the blue continuous line. So instead, the signal appears to have a lower frequency. Now this is the aliasing effect. This demonstrates how undersampling causes loss of information and waveform distortion. As we can see, like in televisions and videos and music, if the frequency is low, we can hear or we can see the distortions. And that is for laboratory activity number 8, sampling and aliasing. Thank you.